Okay, so what we're moving on to now is a very different kind of equation. There's a little bit of factoring involved at times, and a little bit of understanding. Definitely some of what we're doing today will still relate to the polynomial stuff that we've done, but we're moving into something like equations and inequalities that we're going to solve that are very different from the ones that we've been doing, and the method is very different. So again, this is a new method, just like solving polynomial inequalities with something brand new, where you use the sketch. Same with this, okay? And we're going to do 3 to 4 different types depending on how you break it up. The ones we're going to be solving today are fairly simple and straightforward, but they do get much more difficult. And there's a few different types, and every type has a slightly different approach. So like over the next couple of lessons, you need to make sure that you're understanding the methods that are being presented and that you are learning them, okay? Before we start, like I said, we have a sketch here. You don't really need to have an accurate version of this sketch. You just need to watch. This is more of an aside. If you take calculus, this will come up again a little bit. It's not super important for what we're doing. It's going to help our understanding a little bit of the absolute value stuff that we're going to be working with. So for those people who like to have sort of a deeper understanding and be able to visualize these things, it will help. But you're going to be able to solve the questions that we're going to be solving, without this, what we're about to do right now. In the real world, what's the point of math? It's to model real world situations, okay? And we use math all the time in little ways, like I'm going to buy 5 boxes of cookies and they're $2 each, so it's going to cost me $10. Like, that's math, right? But then you get into harder math that builds computers and cars and all that kind of stuff, and all the complicated stuff that happens around our planet. Do you think that in the real world, most situations are going to be modeled by a single function? Like, no, of course not, right? There's no way that a single cubic function or quadratic function will be appropriate to model an entire situation. The profit of a company might be quadratic, and then it peters off, and it becomes some other kind of function, maybe kind of linear or something like that, right? Like, it's going to change over time. The profits of a company go up and down. They don't just follow one path. So they change depending on, the climate of the community and the country and the whole world. So if you're looking at something like that, company profit or whatever, over a long period of time, you would need more than one function to represent that relationship or whatever's happening. Even think about the ones that you did back in grade 10 that are very simple to sort of understand. Throwing a ball in the air, or throwing your eraser, where's my eraser? In the air. Ready, watch. Parabola. That's quadratic, because that's what gravity does, right? Until it hit the ground, it's not quadratic anymore. Now, in grade 10, you only look at the part where it's in the air until it hits the ground. But if we expanded that domain of how we were talking about the speed or the distance or the height of the eraser that I threw, when it hits the ground, the function changes. It's no longer parabolic, because if it was parabolic, it would have gone through the ground and keep going forever, I guess. So what actually happens is I threw it, it went up, it hit the ground, and then it just did that. And it's still doing that. Now it's just on the ground. So the height is 0. Still 0, still 0, still 0, right? So it's 2 different functions. So we have a notation in math to show a single relation or a single representation of something that requires multiple functions. Okay, and it looks something like this. So I'm going to break this up into part A and part B. And so A is what kind of function? It's linear. Okay? And it looks like it has a y-intercept of 3. And it looks like it has a slope of 1. So A is y equals x plus 3. What is B? This is not supposed to be a challenging question. Not what's the equation, what kind of relation is it? It's parabolic, so degree 2 quadratic, right? And again, this, like, you could do this in terms of what we've been doing in this course. We've come up with the equations of polynomials from the graph, but I'm actually going to go back to grade 10 and look at it as a transformation. So this looks like it has a shift to the right by 3, which means it should be y equals x minus 3 squared, or we would call that a turning point x-intercept at positive 3, so it's x minus 3 squared, right? And that would be the equation of that part. And how do I write them as a single function or a single relationship representing what? I don't know what this would represent. Something that a person, it could be, how about this? A person who was like climbing stairs and then got on to some kind of like swing or something, and it swung them down and then swung them back up, and I don't know, they go flying off into space or something. I don't know. So anyway, if we want to write them all as a single function, we do it like this. So notice how f at x equals like both of those. But we're missing something. Yep.
Sorry, is there a 1 by the x?
No, those are commas, which will make more sense when we complete this. It's not finished. We're missing something. It kind of matters when we're using one function and when we're using the other, doesn't it? Because I could change where one ends and the other one starts. So it's x plus 3 when x is less than 1. And it's x minus 3 all squared when x is greater than or equal to 1. The fact that I included the 1 in the second part is irrelevant. I could have included it in the other one or both, I suppose. Okay, but I have to include it in one of them. Otherwise, the function wouldn't exist at 1, but it does. Okay, and again, if you take calculus, you'll learn a little bit more about this. We'll talk a bit more about this kind of thing. But that's that. It's called piecewise function. That's the name of it. It's called the piecewise function, and it's basically a single function made up of more than one kind of relation or relationship or whatever. Does that make sense? So this is gonna kind of help some of the notation that we're gonna do to just think about how absolute value functions work. This is not something you're going to be tested on. Okay, you're never going to have to do this in this course. Write out piecewise functions, but it is kind of a big thing. I did it in like grade 10. We did piecewise linear functions in grade 10. Just I don't know why, but you know the curriculum changes every 10 or so years. So, but it's not really in the curriculum anymore. But it's going to be kind of useful for us today. Okay, so it's just a notation. What we're actually talking about today is absolute value. Who remembers what absolute value means? Only one person, come on. Okay, 2, 3, yep, kind of. Good, okay, yep. What does it mean? Who wants to tell us? Lily? It means that the result is going to be positive, right? So if it's already positive, you just leave it alone. If it's negative, whatever's inside the absolute value symbol. By the way, when something is inside an absolute value sign or a square root sign has another name as well, or something like that, it's called an argument. So that's, again, some language that we'll start hearing more and more throughout this course. So the argument of the absolute value, what's inside the absolute value brackets or the absolute value sign, If it's positive, you leave it alone. If it's negative, you flip it to positive. That's all it does. Okay? So the absolute value of 5 is 5. And the absolute value of negative 5 is 5. So it doesn't flip the sign. If it flipped the sign, we'd just be multiplying by negative 1, and we wouldn't need that symbol. Right? It doesn't always flip the sign. It removes negatives. The absolute value of negative 17 is 17. And the absolute value of positive 17 is 17. Okay? And when you're working with numbers, it's as easy as that. It's the easiest thing we're going to do in this course. When we're working with functions, it's a little bit trickier. Okay? And that's kind of what we're going to be exploring today. The absolute value operation, it gets easy for us to understand. And as I said, if it's a number, if it's the absolute value of negative 5, it's just 5. That's easy for us to do. But what is actually happening? Like, what's the mechanics of what's happening? So the way we are going to think about it is this. If the quantity of the expression inside the absolute value sign is negative, if it's negative, because if it's positive, we leave it alone. But if it's negative, then we multiply b by negative 1. And this is why absolute value operation is a little different from other kinds of operations. Because it's like sometimes we do this and sometimes we don't. Right? So that's kind of tricky. That's kind of tricky. If it's negative, we multiply by negative 1. Like, that's the mechanics of what we're doing to flip it to being positive. But if it's not negative, then we just leave it alone. And no other operation that we've ever explored has that. If it's like, if you're squaring something, you just square it. You just always square it. There's no if this or that, right? So that's going to add the complications to the equations that we're going to be solving. And this is how we can use piecewise function notation to understand this. Again, we're going to start actually solving some of these, and that's what you need to know how to do. But this little introduction might help you just think about why we're doing what we're doing and understand why we're doing what we're doing. And even if it doesn't make sense now, again, you can come back later and just review this, and it might help you make sense of it later. And if you understand why, you're more likely to remember it for a quiz or a test, right? So that's kind of the point of all of this. So if I have a function f at x, that is the argument, but my actual function, I could call it g of x. So this might be a little weird, but g of x equals the absolute value of f at x. So g is a different function. That's the absolute value of f at x. If the function is negative, then I multiply by negative 1. So the thing I would be using in my work is negative f at x. If the function is positive, I leave it alone. So I'm going to use negative f at x when f at x, not x, f at x is less than 0. So if the function results to a negative, I multiply by negative 1. If the function is positive, I leave it alone. So what if our function has an actual thing, has an actual expression? Like, let's not just talk about general functions. Let's look at an example. we have this what if situation. If it's negative, we do this. If it's positive, we do this. So we have two separate cases. And again, maybe a good way of explaining it is like we don't have that button on our calculator where we can just plug in absolute value. You might actually have an absolute value button on your calculator, but it's not going to help with what we're doing. Right? There's no button for it. So we have to be the ones that are kind of managing it. So case number one is going to be if it's negative. And that means 2x minus 6 is less than 0. Whoops. Right? If 2x minus 6 is less than 0, can somebody think of an example of an x value that will make this less than 0? 4? No. 2, thank you. So if I plug 2 in for x, 2 times 2 is 4. 4 minus 6 is negative 2. So there are values for x where this expression will result in the negative. Do you understand what I'm saying? Like that's what I'm talking about. If the expression is negative, so when x is 2 or when x is 1 or when x is 0 or any negative number, the expression will evaluate to a negative. When does this occur? When x is less than 3. So when x is less than 3, then we have to use negative 2x minus 6. Case number 2, when the expression evaluates to a positive, is when the expression 2x minus 6 is greater than or equal to 0. And again, I could put the equal sign on either. It doesn't really matter. Or both for that matter. So I'm just choosing to put it on the second one out of habit kind of thing. We'll talk about this more. It does have to be there, but... So that's when 2x is greater than or equal to 6. Getting ahead of myself. When x is greater than or equal to 3. Then we use just 2x minus 6. We just leave it alone. So once you have that copy down, put your pencil down and think about this for a second. What is it that I'm getting at here? Oh yeah, the eraser that I threw. What is it that I'm getting at here? The absolute value, what it means is, if I put a value less than 3, so let's go with 2. I put 2 in. 2 times 2 is 4. 4 minus 6 is negative 2. But now that I've got the negative sign out in front, that will evaluate to positive 2, right? So I could actually punch it into my calculator, and I'll get the answer of positive 2, which is what we need because of the absolute value symbol. Because it can't be a negative. But if I put something bigger than or equal to 3 in, but we'll go with bigger for now. So if I put 5 in, 2 times 5 is 10, minus 6 is 4. I leave it alone. I don't want a negative sign out front. Right? So when I'm saying, like, mechanically what we're doing, what I'm talking about is if I want to punch this into my calculator and have my calculator do the heavy lifting to get me the answer, I need to know when to add an extra negative and when not to. Okay? And everything that we do in solving absolute value equations and inequalities will break down into this. We have to separate these questions into different cases. The cases where it's negative and the cases where it's positive. Okay, so let's start solving them. First, we're going to talk about the graph. Again, you don't need a nice grid for this. You can just do a sketch. Okay, so here's how we're going to do this. We're going to solve this by graphing, which means I need the left side to be one function. And I'm going to need the right side, and I'm going to write it down here because I need some space to write some other stuff, to be a separate function. And you graphed absolute value functions in grade 11, and so we could graph this with transformations, but that's not how we're going to do it. We're going to think about it as this piecewise function. Where I use negative x minus 1 when the function evaluates to a negative, and I just use x minus 1 when the function evaluates to a positive. When will this evaluate to a negative? Just by inspection. When x is less than 1, so like 0, 0 minus 1 is negative 1, negative 1 minus 1 is negative 2, negative 2 minus 1 is negative 3, so yep, all those numbers. So when x is less than 1, and when x is greater than or equal to 1, it'll evaluate to 0 or a positive, and so we can leave it alone. Okay, so watch how this works. This function is linear. Y equals x minus 1 has a y-intercept of negative 1 and a slope of 1. Is that right? But I only use that function when x is greater than or equal to 1. Is that right? Do you see what I'm doing there? When x is greater than or equal to 1, I'm using that function that I just drew. When x is less than 1, I'm using that one, which is negative x plus 1. So that has a y-intercept of 1 and a slope of negative 1. Is that correct? So there's your y-intercept of positive 1 and slope of 1. So there's your absolute value. Isn't that what absolute value looked like in grade 11? And this is a bit of a different way of graphing it, probably kind of a harder way, but there's a reason why we're doing it. What does g at x equals 5 mean? Maybe I should do this in orange. That's just a straight horizontal line at 5. Throughout the next 3 lessons when we're working on absolute value stuff, like you're just going to solve these by splitting them up into cases. You're going to be doing it algebraically. But again, this is the visual understanding. So what I'm actually kind of doing when I'm graphing an absolute value is I'm graphing one straight line and then graphing the negative of that, because this straight line would have gone below the x-axis and would be negative, right? So I have to multiply it by -1, which kind of reflects it back up above the x-axis. So what are my answers? When does the absolute value of x minus 1 equal 5? There and there. So -4 and +6. Again, we're not going to be solving by graphing, so that's not something you need to know how to do to get marks on tests in this course, if that's what you're concerned about. But it does illustrate why we get two answers, and it does illustrate a little bit about that multiplying by -1 thing that's going to happen over and over and over again, and some people are going to get confused about why, like later, like next lesson or even later this lesson, you're going to forget why we're multiplying by -1 and when we have to multiply by -1. You're going to start multiplying other random things by -1 that shouldn't be. Okay, so this might help you understand why. We're going to visualize a lot of these things. We're just going to use some graphing technology. We're not going to be sketching them all ourselves because it'd be too hard, but it's going to help us understand the different kinds of outcomes that we might get. I don't know that you have to write this down. It'll be on the note. You can write it down if you want. I'm just going to say it quickly, though. You might not have time. But in order to solve algebraically, right, that was graphically. How do we do it algebraically? We have to split the equation into two cases, the one that's negative and the one that's positive. Consider which case goes below the x-axis or which case is going to be negative and manage it, which means multiply by -1 and then solve each case separately. And moving forward, we then have to interpret our answers, and we have to consider whether they're appropriate answers or not, because sometimes we're going to get answers that don't make sense. But that'll be more happening starting tomorrow. So let's try this same example algebraically. Case 1 is when it's negative. When the argument of the absolute value, not the other junk, just what's inside the absolute value symbol, is less than 0, is when we have to multiply by -1. That happens when x is less than 1. I'm just solving that inequality, right? I just move the -1 over. I use this. Because that's what absolute value means. It means if it's negative, you multiply by -1 to turn it back to a positive. If x minus 1 is greater than or equal to 0, which will occur when x is greater than or equal to 1, I just leave it alone. Now, the reason this works is because I've defined my cases separately. I've defined this case on the left as the case when it works out to be a negative. When x is less than 1, I'll use this. When x is greater than or equal to 1, I'll use that. So I've separated my cases and defined it that way. So when I solve them, I'm going to get proper solutions kind of thing. So how do we solve this one? I hope that's pretty easy. Same two solutions that we got when we graphed it? Yep. Of course, it has to be. Is -4 less than 1? Yep. Is 6 greater than or equal to 1? Yep. Think about what this means. If I take -4 and I sub it back in, -4 minus 1 is -5. What's the absolute value of -5? 5. So they're equal. And I had to multiply by -1 to get it to turn into a 5, like a positive 5, didn't I? Like it gave me -5. When I sub in the -4, my result is -5. When I sub in 6, 6 minus 1 is 5. Absolute value of 5 is 5. 5 equals 5. Yeah, right? So both those values do work. Which you could solve by inspection. You probably could have just figured that out. But, you know, if you have to do more complicated ones, then it's useful to have a method. Any questions? We're really only going to do one more example because the rest of them today are easy like this. They're just equal to a constant. So equals 9 makes it easy. If it's equals 9x, it becomes more difficult, and that's what we're going to do in the next lesson. But these ones are pretty straightforward. Yep.
On the quiz, it's just today's 2 lessons.
We'll talk about that after, okay? Okay, so what do? Break it up into 2 cases. Case 1 is when the argument of the absolute value is less than 0. So I'm moving the 4 over. Then what do?
Divide both sides by 7 and flip the sign.
Divide both sides by -7, and because it's negative, we have to flip the sign. Very good. Whoops. So I get 4 over 7. What this is saying is when x is greater than 4 over 7. What's 4 over 7? It's about a half. Okay? When x is bigger than that, this will result in a negative, which makes sense. So if I put a 2 in for x, I'm going to get 4 minus 14. If I put 3 in, I'm going to get 4 minus 21. The bigger x gets, the more negative we're getting, because we're subtracting the x in this case. Okay, so when x is bigger than 4 over 7, I'm getting a negative, so I have to multiply that part by a negative. So when 4 minus 7x is greater than or equal to 0, is when I'm not going to multiply by a negative. Again, I'm dividing by -7. Flip the sign. And in this case, I just leave it alone. And now I just solve these. (13 over 7 is greater than 4 over 7? Yep. (-5 over 7 is less than 4 over 7? Well, it's negative, so yes, it's less than. You don't even have to do the fraction math there, right? So we've got 2 solutions again. Any questions? we have one more thing to do that's sort of different from this. Yep.
Wait, why is the 5/7 negative?
Because that's just, well, it's negative because that's how it worked out. But look at what I started with. So I subtracted 4 from both sides. 9 minus 4 is 5. I've got a negative 7x. When I divided by negative 7, it made the result negative. Okay. I think this is the one that we already graphed, so it's kind of weird that we're graphing it again, I guess. But the way we're going to sketch these is actually a bit different from how we were doing it before. So before I did a piecewise function, and we talked about 2 different functions, but here's what we're actually going to do. So, whoops, sorry, I'm moving around too fast. I'm going to graph y equals x minus 1, which has a y-intercept of -1 and a slope of 1. Okay? So it looks like this. And again, it's not on a grid. This is just a sketch. So we're going to label things, but it doesn't matter exactly where you line stuff up, if you understand what I mean. So watch. Just put your pencil down for a second and watch. I'm starting up here. And when I hit the x-axis, I start drawing a dotted line. Because absolute value means you don't go below the x-axis. And I take that dotted line and I reflect it above. So I try to match it on the other side. We have to label. So this is 1, my x-intercept. Watch, folks. What's that point there? -1. It's the y-intercept of that thing that we just graphed. So this is -1. So what's that? +1. Good. Not super interesting when it's a linear. So let's try something a bit more interesting. What are my x-intercepts? -3 and 1, both order 1, both straight pass-throughs. What's my y-intercept? Careful. Yeah, it's going to be 3, right? When you actually, so of the part inside, it's -3, but it's actually going to be 3. But here's another thing that you can do. If you're struggling with the y-intercept, just sub in 0. So the y-intercept of the actual function is going to be 3, but that -3 is going to be important. Okay, so I've got x-intercepts of -3 and 1. Again, watch how I'm going to draw this. Then I take that dotted part and reflect it above. So there's the -3, but the actual y-intercept is +3. What do you think? So if I ignore the absolute value symbols, this is x squared plus 2x minus 3. It's a quadratic. It's a parabola. So it would look like this. Right? But as soon as I go under, like the strategy for graphing these nicely is as soon as I hit the x-axis, I start doing a dotted line, and then I just try to sort of replicate it with a solid line above, because the solid line is our actual function. Okay, one more. What's going on with this one? Okay, good. First one was in factored form. This one's in expanded form. This is all stuff we know how to do. If we're going to sketch in expanded form, what do we want to do? Factor. Okay. So let's do that. And you're right, we take an x out. It doesn't disappear, we still have it. And now what do we have? Difference of squares. So I've got 3 x-intercepts, -2, 0, and 2. My y-intercept is no. 0. Careful. Okay. So now I can sketch this. It's degree 3, positive leading coefficient. I'm only looking at the part inside the absolute value symbol. I'm not thinking about the absolute value part yet. Positive leading coefficient, degree 3. So I know the end behaviors. I'm going to mark my x-intercepts. -2, 0, +2. I'm going to start down here, which means I'm dotted. Just look at that function quickly. That's the one that we were graphing all of Unit 1. It's just like if you imagine those dotted lines to be solid, that's what that function would look like. Like that should be familiar to us. But if I'm below the x-axis, I just do it dotted. And then watch. Again, I trace it above like that. Any questions?